Hi, good day. For today's discussion lesson 10, we will be tackling multiple life function. But before we proceed, we must recall this following concept since we will be using this later on. First is the lifetime distribution function and the survival function. Second is the force of mortality and the mean variance. So to proceed with our first death case scenario, we have joint life status. So by means of XY, we mean two people. And magfe-fail yung kanilang joint life status kapag ang isa sa kanila ay namatay. Their future random variable and life distribution and survival function is defined below. So life distribution gives us the probability that at least one of them dies at a specific time, and the survival functions give us the probability that both are alive after time t. So to move forward, we have last survivor status. So the future random variables as well as the force, mortality, and density function is defined below. Now, here are some fundamental symmetric relations. Random variable states that joint future lifetime is just the sum of their individual lifetime. It also follows for survival, distribution, and this density function. And it follows additive relationship between individual survival probabilities or the probability of them dying. Now, when t sub x and t sub y, the future lifetime, are independent, we use the following. The survival probability means that the probability that both individuals survives is just a product of their individual probabilities. It same goes with the death probability. Note that when dealing with joint life status, P is more convenient since we are tracking that both of them are alive and vice versa. So for example, number one, we have the future lifetimes of 50 and 50 and they are independent. So we are expected to find the following. So first step, we have to find the probability that the age 60 dies before reaching age 61. Then after this, we will find the probability of age 50 survives at age 60.7. And lastly, to compute for the joint survival status, i-squared na lang natin kung ano yung nakuha nating probability. Hence, we get 0.8208. And for letter B, note that this is independent. So the force of mortality is defined by the sum of their individual force of mortality. Hence, we get 0.02779. So for example number 2, so we are expected to compute for the last survivor status. For a last survivor status, it is easier to operate on Q. So we will get the product of their individual probability of that function. Hence, we get the answer 0.985796.
The force of mortality for the last survivor status isn't just the sum of individual mortality rates. We need adjustments for survival probability. First, we take each person's survival probability and multiply it by their mortality rate. Then, subtract an adjustment for cases where both survive together. Finally, we divide by the probability that at least one is still alive. Unlike probability densities, mortality forces don't add up neatly. We need this adjusted formula to account for joint survival. Let's calculate the force of mortality for the last survivor status of two lives 40 and 50 at time 10. We start with De Moivre's law, which helps us determine the individual force of mortality. For the second life, age 50, this is straightforward. Using survival probabilities, we also calculate the force of mortality at age 60. Next, we need the joint survival probability, which we compute using the product of survival probabilities for both lives. This helps us determine the joint force of mortality. Finally, plugging in everything into the formula, and after simplifications, we get an answer. This result is interesting because it's smaller than the individual forces of mortality, making sense since in the last survival scenarios, at least one person is still alive, lowering the overall rate at which this status ends. Let's go over some key definitions related to two lifetimes. First, the mean of two lifetimes. The expected value of the sum of two lifetimes is just the sum of their individual expected values. Next, the covariance of two lifetimes. The covariance of the individual lifetimes plus a correction term that accounts for how their expected values differ from their joint lifetime. Now, if the lifetimes are independent, the covariance simplifies to the product of the differences between the individual and joint expectations. Finally, the variance of the joint lifetime. It's the sum of individual variances minus twice the adjustment term we saw in the covariance formula. Let's solve for the variance and covariance of the minimum lifetime when two independent lives are subject to constant mortality rates. Since both lifetimes follow exponential distributions, their minimum also follows an exponential distribution with a combined rate of 0.05. Using this, we can quickly find the expected value and variance of T sub x1. The variance is simply the square of the inverse rate, which gives us 400. For the covariance, we use the formula that relates the individual life expectancies to the joint expectation. Plugging in the values, we again get 400. So, both variance and covariance turn out to be the same in this case, which makes sense because the formula accounts for how the lifetimes interact.
Now, let us consider the probabilities wherein we consider the order of death of these life statuses. We define the life statuses with the following notations. The first notation indicates that X dies before Y, hence the 1 before X. In contrast, the second notation indicates that X dies after Y, hence the 2 before X. The probabilities of these statuses are given by the following. We also note that the probability when X dies before Y is equal to the probability when X dies after Y plus the probability when X dies within T, but Y survives more than T. To specifically solve for these probabilities, we consider the joint density function of the future lifetime of X and Y, assuming that lives are independent. For the first equation, we consider that the probability that Y and X survives to U years and the force of mortality of X at U. For the second equation, we consider the probability that X dies within U, Y survives to U years, and the force of mortality of Y at U. Now let us consider to solve for the example 10.5 given the following. For the first method, we calculate by conditioning which number is on top of the notation. We observe that the person aged 98 dies first before the person aged 80. We then use the second equation discussed. Assuming the Mauvois law, we get the following probability density functions. Consider that the probability of the person aged 80 dies within U, the probability of the person aged 98 to live within U, and its force of mortality. Solving for the following, we get omega equals to 110. For the second method, we solve for the probabilities graphically considering its area. Since the joint distribution of age 98 and 80 follows the Mauvois law, it is a bivariate uniform over the area of the rectangle. And the event where age 98 dies before age 80 is the area of the triangle like so. According to statement 2, the probability that age 98 dies first before age 80 is 0.8. Then its complement, the age 98 dies after age 80 is 0.2. Since the probability is proportional to the areas, we get the following. Hence, we get the same answer of omega equals to 110.
In actuarial science, we use fully continuous models to calculate expected payouts. On the screen, we can see the formulas for joint life insurance and end-year term insurance, which are essential for pricing policies covering multiple lives. Now, let's move on to definition 10.12. This is commonly used in pension plans, spousal insurance, and business partner policies. It simplifies calculations by expressing joint life insurance in terms of individual life insurance values. And it ensures fair pricing and accurate risk assessment for insurers. Next, we have definition 10.13 as we can see in the screen. This is applied when two lives are insured together, helping measure how their survival times relate. It calculates dependence between insured lives, which is crucial for pricing joint life and life survival benefits. Lastly, it helps insurers assess risk and ensure they hold adequate reserves for payouts. Now, let's apply this to example 10.6. We analyze a 5-year term insurance payable on the last survivor's death for two independent lives, where X mortality rate is 0.01, Y mortality rate is 0.03. Our goal is to calculate APV, variance, and covariance. For APV, we use definition 10.12 and apply the annual term insurance formula we learned from previous semesters. For variance, we use the standard variance formula. And for covariance, we apply definition 10.13. As we can see, the covariance is positive. It suggests that while X and Y are independent, their expected payouts move together slightly rather than being completely uncorrelated.
In previous lessons, we had discussed the relations between annuities and insurance for single life cases. Here, we extend these concepts on multiple lives cases, where on both equations, the continuous annuity can be obtained when given continuous insurance and the force of mortality delta. Moving forward, let us also discuss the insurances and annuities for fully discrete multiple life cases. Here, we can see the format of equations for both joint life and last survivor status seems familiar as it follows the insurance and annuity equations of the single life cases. Only that, in joint life and last survivor status, we consider two lives. For the fully discrete insurance of multiple lives, we have the summation of the discount factor V raised to K multiplied to K deferred Q of the two ages. Meanwhile, for the fully discrete annuity of multiple cases, we only consider the discount factor and the survival probability of the two ages. Now, let's consider this example. Given a life table, we are asked to calculate the APV of ages 60 and 63 under a 3-year term life insurance, which pays a benefit amount of 1,000 at the end of the year of the second death or at the end of the third year. To solve this, let's start by getting the 3-year temporary annuity of each age. After this, we clump them by multiplying expressions with the same value of A, giving us 2.69885, but this is in terms of joint life status. In terms of last survivor status, by the symmetric relation, we have 2.782130. Using this value, we solve for the APV of the 3-year term life insurance on two independent lives and obtain 793.9163. Next is the reversionary annuity, which refers to the payment of unit rate per year while Y is alive and X is dead.
For the contingent insurance, it depends on the order of death between two individuals, X and Y. First death insurance pays a benefit when X dies first, while second death insurance pays a benefit when Y dies after X. Example 10.8 deals with the last survivor insurance, where premiums depend on the number of alive individuals. We have higher premium 3P when both insured individuals are alive, while we also have here the reduced premium P when only one remains. Using the equivalence principle, the goal is to determine the value of P. For the method 1, we will solve the probability that only one insured is alive. Using this, the APB equation is set up by summing the present values of premiums, leading to 8.179829P. And for the second method, it decomposes the annuity into a last survivor annuity and a joint life annuity to achieve the same result. Finally, solving P, we will get 97.057, which is the required premium.
For example 10.9, given that A sub x bar is zero point 0.4 and A sub xx bar is zero point 0.6, we will find the second death contingent insurance where the death benefit is paid upon the death of the second X. Since both lives are the same age and subject to the same mortality, this simplifies to mu sub xx plus t equal to 2 times mu sub x plus t. Solving this and applying, then substituting the formula of the second death contingent insurance, we will get 0.1. And now we will proceed on amply payable multiple benefits, which is divided into two sections. First is empty life insurance, where it tackles how to adjust life insurances and annuity calculation when payments happen more often than yearly or say monthly. Now, instead of assuming that the death benefit is payable at the end of the year of death, we may assume that it's payable at the end of the month of death or even the week of death. The first two formulas are used assuming these are independent lives and follows UDD. The third and fourth formulas assuming these are non-independent life and follows UDD. On the other hand, Woolhouse formula is simply an alternative approximation method, specifically for annuities that doesn't rely on the UDD assumption. And presented here is the formula for the Woolhouse. Next slide is the definition 10.20 that focuses on the dependent lives but excludes the common shocks. Step 1 expresses the transition probabilities in terms of occupancy probabilities. This establishes the mathematical relationship between being in a state at a specific time and the chance of moving to another state. Step 2 expresses probabilities and benefits like insurance payouts or annuity payments in terms of transition probabilities. This sets up the calculation of EPV, and this model can be used in various situations such as pricing joint life insurance, valuing supervisory benefits, modeling disability, as well as health insurance. And that would be all. Thank you.